In section 16.7, we discuss surface integrals. Let's set up the context in which all of this is going to happen first. So let S be a surface. I am not doing a very good job of writing. Given by vector function R of uv, where u and v range over a region D. So we have over here in the UV system, I might go ahead and draw it as a rectangle, but it won't necessarily always be a rectangle, but close enough. So region D, and then over here, 3 dimensions. And I will draw a surface that perhaps fails the vertical line test, so won't necessarily be giving z as a function of x and y. So R, of course, goes from points uv over to points in the xyz plane. And in this context, we define and investigate two types of integrals. The first is a double integral over S. So by the way, I did not label that clearly. This is the surface S over here. The double integral of a scalar function, f of x, y, z, ds. Before I go on, let me just say that we've now got enough variables that I cannot draw pictures of, rectangles or anything else that illustrates a Riemann sum here, because if we are integrating over a 3-dimensional region, then that means in order to, draw all of this out, you would have W equals F of X, Y, Z, and that's 4 dimensions, and we can't draw 4-dimensional pictures. So everything just has to go back to definitions. You're, comfortable with the 2 and 3-dimensional cases, and that has to be enough to get you to accept what's going on in this context. And then the other type of integral that we will look at is the double integral over S of a vector field dot ds, S with a vector notation here. And what this is the double integral over S of f dot n ds. I'll note out here that f is a vector field. Since I'm running out of room, you've seen it before. Lowercase n is normal to the surface out here, so we could draw an n like that, relevant for this case here. Okay, so what we're going to do in part one of the lecture is focus on the integral of the scalar. And looking at my notes, yes, it's starting in part two. I think I'll probably have parts 2, 3, and 4. The longer amount of time will be spent investigating the integral of the vector field over a surface. But right now, case one. All right. So let me just start off by saying what it is we're going to do to integrate this scalar function f over this surface. So the double integral of f of x, y, z ds is, by definition, the double integral over d of f, where we parameterize out in terms of u and v, times the magnitude of ru cross rv dA. Of course, what this means is the function r is going to be given as, x as a function of u and v plus y as a function of u and v plus z as a function of u and v. And so what you do here is everywhere in f that you see x, you replace x with x as a function of u and v. And you go in and do similar things for y and z. You multiply that by the magnitude of the cross product, ru cross rv. We ran into this in section 16.6. This then is an integral. This takes the integral of f over s and gets it back to an integral over d. So we're now, and so since d is two-dimensional, that's why this is an integral dA. And so, I mean, at the end of all of this, this is a, chapter 15 integral. It's an integral with respect to area. So, if we have a rectangle, then of course that's both type 1 and type 2. You'd have to investigate whatever you have over here. All right, let's see. I want to make some notes about all of this. Viewed properly, this should look familiar. Why should it look familiar? Well, go down a dimension, and I won't take time to introduce all of the formal notation, but recall the integral of f of x, y ds the integral of a scalar over a curve, not a surface, was the integral from A to B of f of r of t times the magnitude of r prime of t dt. So if you're familiar with this, this is the extra dimension generalization. We switch over from magnitude of r prime to the magnitude of the cross product of the partials and so forth. Okay, so hopefully, you don't feel completely out of context. There's some similarities there. Also, when f of x, y, z equals 1, then that just tells us, so what is all of this when f is 1? Then this tells us that the double integral over s ds is the double integral over d. Of course, this is still 1, and so then this is magnitude of r sub u cross r sub v dA. And this should look familiar from 16.6. It's the surface area of S. So again, a little bit of a familiar context. Makes sense that the double integral over S ds gives us the area of S. Okay, and we've seen in previous sections that there's the special case. I'm finally now into the habit of not drawing the special case initially, but the special case is where S is given by z equal to g of xy. Try to remember to use g since we've already used f. So in other words, the special case is where this graph here would pass the vertical line test. So then x and y are the parameters. And we can take S to be given by R of xy equal to xi plus yj plus g of xy k. And this is the sort of thing that we ran into again in the previous section. And so since we've already computed the magnitude of RU cross RV for this special case, I'm just going to go ahead and throw out what that is. So then in this case, the double integral over S of xyz ds is the double integral over d of f. Everywhere I see an x, I replace it with x. Everywhere I see a y, I replace it with y. So replace in quotes. Everywhere I see a z, I replace it with g of xy. And then I multiply by magnitude of the cross product, which we calculated more than once, I believe, in the previous section. Z sub x squared plus z sub y squared plus 1 dA. And this should also look familiar. This should, you should go back and compare to arc length integral. Instead of writing it out, if you don't, if you can't visualize it, in 16, I guess it was 0.2. Okay, so enough, enough introduction, enough hopefully context. Let's now look at an example. I will work problem number 11 from the exercises in section 16.7. We're asked there to evaluate the double integral over S of x squared z squared ds, where S is the part of the cone, z squared equals x squared plus y squared, that lies between the planes z equals 1 and z equals 3. So we're only interested in the upper half of the cone, since that's the only part that would be between 1 and 3. So let me just see if I can do a reasonable job here. Let's see. So the surface S is that part of the cone that lies between z equals 1 and z equals 3. I perhaps should not shade anything in here. The top and bottom, the caps, or I guess the top and bottom, they're not part of the surface, but good to kind of indicate that it's intersecting those planes, and the only part of the surface is the cone. Okay, well, the first thing you should ask yourselves in any case is this the special case? Is this the case where the surface we're integrating over is given as a function of x and y? Does this surface pass the vertical line test? And the answer is yes. This is the special case. Z is equal to g of x and y here. So, of course, in order to solve for z, we would take square root of both sides. Z initially should be declared to be the plus or minus square root. The only reason we can get rid of the minus is because we know that the negative square root does not come up here above the xy plane. So That's a better reason for not having the minus than forgetting that there's even the possibility of the minus. So since z is greater than 0, the surface is given by the positive square root of x squared plus y squared. So I will, let's see, and let's go ahead and say what values, see, we know that z goes from 1 to 3. So yeah. Whoops. I just said 1. Didn't write it. I will quickly note what z sub x and z sub y are here. You can go through and verify, but we've seen these cases before. Get some 2's canceling out and algebraic simplification along the way. So then, so what I'm setting up here is now, did I never write out? Oh, here it is. Here it is. What I'm setting up is this integral here. So I'm computing z sub x, so I need to compute this multiplier, which helps us get arc length, surface area. So then the square root of z sub x squared plus z sub y squared plus 1 is the square root of x squared over x squared plus y squared plus y squared over x squared plus y squared. And I can see now, if I'm going to add 1 to these, then I should write that 1 with a common denominator. So I'm going to go ahead and write that as x squared plus y squared over x squared plus y squared. This is then, how about I just let you play around with the simplification there. You end up getting square root of 2 out of all this. So then our double integral over d of f of x, y, g of x, y, and so forth becomes the double integral of x squared, and then I replace z. We replace z with g of x, y, which is this. And so perhaps I should have noted, I mean, this is my g of x, y. So, so then I've got z squared, see? So that's square root of x squared plus y squared squared, and then square root of 2 d8. And the region D over which we're integrating, so of course we're going to simplify this. So times x squared plus y squared square root of 2 comes out front, dA. But the region D is this region here. So this is our D. So it's polar. So we're going to have to go polar here. So then the question is, what's the radius of these two circular disks? You can tell it's going to be a circular disk in each case. Well, one of them is 1 squared equals x squared plus y squared. The other one is c equals 3. So that's 3 squared equals x squared plus y squared. So disks of radius 1 and 3. So we can describe D as being a function of r and theta. So 1 less than or equal to r, less than or equal to 3, theta going 0 to 2 pi. So then this is the square root of 2, integral 0 to 2 pi, integral from 1 to 3 of, and this would be r squared cosine squared theta times r squared cosine squared theta plus r squared sine squared theta. Then dA for polar is r dr d theta. And this wouldn't be a bad time for you to press pause and see if you can work through this integral. I will pause for half a second for you to press pause. And I hope you did that and found all the simplification. Factor r squared out of this, and sine squared plus cosine squared is 1. So then you can factor the integrals. This becomes square root of 2, integral 0 to 2 pi of cosine squared d theta times the integral from 1 to 3. You get r to the 4th times another r, so r to the 5th d theta square root of 2, integral 0 to 2 pi. Cosine squared, we use the half angle identities. This one over here, of course, goes quicker. All right, so square root of 2, integral, let's see, I guess I went a little quicker in my notes than I'm indicating that I'm going to go here. Go ahead and evaluate the integral here. So antiderivative of 1/2 d theta is just 1/2 theta plus the antiderivative of cosine of 2 theta over 2 is sine of 2 theta over 4. All of this from 0 to 2 pi. This is now 1/6 times 3 to the 6th minus 1. And let's see, square root of 2 over 6. Plug the 2 pi in, we get pi plus 0 minus, and then a bunch of zeros, times 3 to the 6th minus 1, which is 728. So I'm getting square root of 2 times pi times 728 over 6, which is square root of 2 pi times 364 over 3. All right. That's enough. Integrating. All right. So that's where I'm going to leave our discussion of integrals of scalar functions over surface areas. There's really, no more interesting parts of the story to cover. You'll just go through a similar process. The only thing that you'll have to be aware of is sometimes you have to go through this process for these general variables R of U and V. I apologize for indulging. And I will see you in part 2 for our beginning of our discussion of the integral of a vector field over a surface.